laws of physics are generally considered non-negotiable, but Soviet aviation engineers often treated them as mere guidelines to be circumvented with enough titanium and raw thrust. Nowhere is this more evident than in the existence of the Sukhoi Su-33. Imagine taking a heavy air superiority fighter, a machine designed to patrol the vast borders of the largest country on Earth, a specialized predator built for high-speed interceptions and long-range patrols, and deciding that its natural habitat is actually a cramped, vibrating steel deck in the middle of the North Atlantic. The Su-33, known to NATO as the Flanker D, is a contradiction in terms. It is a land-based monster forced to live at sea, a massive air superiority fighter operating from a carrier that lacks the one thing usually required to launch massive air superiority fighters: a catapult. When you look at a U.S. Navy supercarrier, you see a carefully choreographed ballet of steam and hydraulics flinging aircraft into the sky. When you look at the Su-33 launching from the Admiral Kuznetsov, you are witnessing a triumph of brute force over aerodynamics. There is no steam piston to accelerate the jet. There is only the pilot, the throttle quadrant, and a curved ramp at the bow that looks deceptively like a ski jump. To get a 30-ton fighter airborne off that ramp requires a level of engine performance and aerodynamic efficiency that borders on the magical. It is an aircraft that shouldn't work. It is too big, too heavy, and operates from a platform that is too small and technically troubled. And yet, it flies. It is the physical embodiment of the Soviet Union's late Cold War naval ambition. Grand, imposing, technically brilliant in isolation, but compromised by the crumbling infrastructure supporting it. To understand the Su-33 is to understand the difference between carrier-capable and carrier-suitable. Any aircraft can land on a carrier if you have a strong enough hook and a reckless enough pilot. But to operate effectively, to fight, to sustain operations at sea, that requires a machine that has been fundamentally reimagined. The Su-33 is not just a Su-27 with folding wings. It is a complete re-engineering of the flanker DNA, a mutation forced by the specific, brutal requirements of ski jump operations. It represents a specific moment in history where the Soviet Navy decided that they didn't just want to defend their fleet with helicopters and vertical takeoff jump jets. They wanted to project power with the same heavy fighters that terrified NATO planners in Central Europe. It is a magnificent, flawed giant, a creature of compromise that somehow manages to be one of the most visually imposing aircraft ever to trap a wire. The origins of the Su-33 lie in the Soviet Union's realization that their existing carrier aviation, based around the Yak-38 forger, was a dead end. The Yak-38 was a vertical takeoff and landing capability demonstrator masquerading as a fighter. It had no range, no radar worth mentioning, and a payload capacity that could be rivaled by a well-packed station wagon. If the Soviet Navy wanted to protect its ballistic missile submarine bastions from U.S. Navy carrier battle groups, it needed a real fighter. It needed speed, range, and a powerful radar. It needed the Su-27. But the Su-27 was a land-based aristocrat, requiring long, pristine concrete runways. Adapting it for the sea was not a matter of modification, it was a matter of metamorphosis. If deep dives into the strategic and technical decisions behind modern fighters interest you, subscribe. There are plenty more aircraft worth examining closely. The design philosophy of the Su-33 was dictated by the limitations of the ship it would fly from. The Admiral Kuznetsov was designed with a ski jump ramp instead of steam catapults. This decision, driven by technical complexity and the Soviet preference for avoiding the massive steam generation requirements of catapults, defined everything about the Su-33. A catapult can force a brick to fly if you push it hard enough. A ski jump requires the aircraft to fly itself. It requires lift, and it requires it immediately. This requirement for immediate lift at low speeds led to the Su-33's most distinctive visual feature, the canards. These small foreplanes, mounted on the leading edge extensions just forward of the main wings, are not just there to look cool. On the land-based Su-27, the long, elegant fuselage generates a significant amount of lift, but the aircraft is statically unstable in a way that requires careful management at high angles of attack. On the Su-33, the canards serve a critical aerodynamic function during the launch and recovery phases. When the aircraft leaves the ski jump, it is flying at a speed that would cause a normal fighter to stall and fall into the sea. The canards, working in concert with the stabilators and the flaperons, generate a vortex that energizes the airflow over the main wing, delaying the stall and allowing the aircraft to fly at much higher angles of attack. They essentially trick the air into sticking to the wing when it really wants to separate. Furthermore, the canards solve a specific problem related to the flanker's massive radar. The N-001 radar in the nose is heavy. On a carrier approach, you want to come in as slowly as possible to reduce the strain on the airframe and the arresting gear. But if you slow down a standard Su-27, the nose wants to drop. To keep the nose up, you have to trim the tailerons up, which pushes the tail down, but also reduces overall lift. It's a fighting match between pitch and lift. The canards change this equation. They provide lift forward of the center of gravity, holding the nose up while adding to the total lift rather than subtracting from it. This allowed the Su-33 to approach the deck at around 240 kilometers per hour, comparable to the much smaller F/A-18, despite being a significantly larger and heavier aircraft. The structural changes required to turn a flanker into a sea flanker were extensive and heavy. The landing gear, for instance, had to be completely redesigned. A carrier landing is often described as a controlled crash, but in the case of a heavy fighter like the Su-33, the violence is extreme. The aircraft slams onto the deck with a sink rate of up to 7 meters per second. The standard Su-27 landing gear would simply snap or punch through the wings under these loads. The Su-33 features a reinforced twin-wheel nose gear unit and massively beefed-up main gear struts with complex oleo-pneumatic shock absorbers designed to dissipate that kinetic energy without rebounding the aircraft back into the air. This added weight, but it was the price of admission to the Carrier Club. Then there is the matter of size. The Su-27 is huge. Its wingspan is nearly 15 meters. Parking such a beast on a carrier deck is a logistical nightmare. To fit into the hangar lifts and maximize deck parking, the Su-33 was given a complex folding wing mechanism. Unlike the F/A-18, where just the tips fold up, the Su-33's wings fold at about mid-span, and the horizontal stabilizers fold as well. Even the Stinger tail boom, that distinctive protrusion between the engines, was shortened and hinged to fold upward, primarily to prevent it from striking the deck during high-alpha landings, but also to shave off precious centimeters of length for the hangar elevators. The engineering required to make these folding joints rigid enough to withstand 9G maneuvers in flight, yet reliable enough to fold and unfold in salt spray and freezing winds, is a testament to the Sukhoi Bureau's mechanical ingenuity. Propulsion is provided by two Saturn AL-31F Series 3 engines. These are not your standard flanker engines. They were modified specifically for the grueling environment of carrier operations. The most critical modification is the special mode, or emergency power setting. During a ski jump launch, especially with a heavy combat load or in low wind conditions, every newton of thrust matters. The Series 3 engines can temporarily exceed their standard afterburner rating, pushing out nearly 12,800 kilograms of thrust each. This mode is thermally destructive. It eats into the engine's service life aggressively, but it provides the kick necessary to get the aircraft off the ramp and into the air. The throttle control system was also adjusted to allow for more precise, rapid response during the delicate dance of carrier landings, where a split-second lag in spool-up time can mean the difference between catching a wire and striking the ramp. However, the physics of the ski jump impose a harsh penalty on the Su-33's operational reality: weight limits. On a catapult carrier, the ship does the work of accelerating the plane. On a ski jump carrier, the plane does the work. This means that while the Su-33 has a maximum takeoff weight of around 33,000 kilograms on paper, achieving that off the Kuznetsov is a matter of specific conditions. To launch with a full fuel load and a heavy weapons load, the Su-33 has to use the long launch position, 195 meters, on the deck. But using the long launch position disrupts the entire deck cycle, preventing other aircraft from landing or launching from the forward spots. From the short positions, 105 meters, the Su-33 is severely restricted. It often has to trade fuel for weapons or vice versa. It can launch with a full air-to-air loadout, but with reduced fuel, necessitating immediate aerial refueling if it wants to go anywhere. Or it can launch with full fuel but a lighter weapons load. This limitation fundamentally restricts the Su-33's utility as a strike platform compared to its catapult-launched peers. The avionics suite of the Su-33 reflects the era of its birth, the late 1980s Soviet Union. It retained the Enderozo-1 radar of the Su-27, slightly modified for operations over water as the Enderozo-1K. This radar was powerful for its time, capable of tracking large targets at range, but it was fundamentally an air-to-air system. It lacked the sophisticated ground mapping modes and multi-target engagement capabilities of contemporary Western radars, like the APG-70 or the APG-73. The Su-33 was designed as a fleet defender, an interceptor meant to kill incoming Tomcats and Hornets. It was not designed as a multi-role strike fighter. Its air-to-ground capability was initially limited to dumb munitions, unguided bombs, and rockets. The pilot had to rely on visual acquisition and the optical sight for ground attacks, a dangerous proposition in modern contested airspace. One of the most interesting yet often overlooked systems on the Su-33 is the OLS-27K infrared search and track system. Located in front of the cockpit canopy, this eye allows the Su-33 to track targets passively without emitting radar energy. In the context of a carrier battle group, where managing electromagnetic emissions is key to survival, the ability to sneak up on an adversary using only thermal tracking is a significant tactical advantage. The OLS-27K also includes a laser rangefinder, which provides firing solutions for the cannon and unguided rockets, giving the Su-33 a surprising amount of accuracy with unguided weapons, provided the weather is clear. The cockpit of the Su-33 is a classic Soviet workplace. Analog dials, steam gauge instrumentation, and that distinctive turquoise-blue interior paint designed to reduce pilot fatigue, or so the theory goes. It is functional, rugged, and completely lacking in the glass cockpit ergonomics of modern Western fighters. The pilot sits high with excellent visibility over the nose, crucial for carrier landings, but the workload is high. There are no large multifunction displays to fuse sensor data. The pilot has to mentally integrate information from the radar scope, the warning lights, and the HUD. It is a machine that demands a high degree of pilot skill, not just to fly, but to fight. Operational reality for the Su-33 has been inextricably linked to the fortunes of the Admiral Kuznetsov. The aircraft entered service in the mid-1990s, just as the Russian economy collapsed. Production was cut short after only around 30 to 35 airframes were built. For years, the Su-33 regiment sat on land, flying rarely, while the Kuznetsov rusted at the pier. The skills required for carrier aviation are perishable. Without constant practice, pilots lose the edge needed to land on a pitching deck at night. It wasn't until the mid-2000s that the Russian Navy began to revitalize its carrier operations, and the Su-33 finally began to see the open ocean. The deployments to the Mediterranean provided a stark look at the Su-33's capabilities and limitations. The aircraft proved to be robust and reliable in terms of airframe availability, but the carrier itself was the weak link. The arresting gear on the Kuznetsov is a source of constant anxiety. During the 2016 deployment off the coast of Syria, 2 aircraft were lost, one MiG-29K and one Su-33. The Su-33 loss was particularly illustrative of the unforgiving nature of carrier operations. The arresting cable snapped during the landing. On a U.S. carrier, there is usually enough deck space and catapult power to bolter, to go to full power, and take off again if the wire is missed. But if the wire snaps after it has slowed the aircraft down, but before it stops, the aircraft is left in a low-energy state with not enough runway left to stop and not enough speed to fly. The pilot ejected safely, but the airframe was lost to the Mediterranean. These incidents highlighted the fragility of the entire system. The Su-33 itself performed well in the air, conducting combat patrols and, surprisingly, strike missions. To overcome the lack of precision-guided munitions capability, some Su-33s were retrofitted with the SVP-24 Hephaestus targeting system. This is not a new radar or a targeting pod, but a specialized computing system that calculates the release point for unguided bombs with extreme precision, factoring in aircraft speed, altitude, wind, humidity, and ballistics. It allows the Su-33 to drop dumb iron bombs with accuracy approaching that of guided munitions, provided the target is stationary. It was a clever, cost-effective solution to a lack of modernization, allowing the old interceptor to act as a bomber over Syria. However, the operational record also exposed the strategic mismatch of the Su-33. It is too big for the Kuznetsov. A carrier air wing relies on cycle times, how fast you can launch, recover, refuel, rearm, and launch again. The Su-33's massive footprint clogs the deck. Its need for the long launch position for heavy loads disrupts the flow. Its maintenance requirements are significant. While it offers incredible range and payload on paper, the constraints of the ship mean it rarely flies with either. It is a Ferrari being used to deliver pizza in a city with speed bumps. Given the operational difficulties and the eventual shift back to the MiG-29K, was the Soviet obsession with heavy carrier fighters a strategic error or a necessary step in learning carrier aviation? Let me know in the comments. The comparison with the Chinese J-15 Flying Shark is inevitable and illuminating. When the Soviet Union collapsed, a prototype of the Su-33, the T-10K3, remained in Ukraine. China acquired this prototype and reverse-engineered it to create the J-15. Visually, they are almost identical. But the J-15 benefits from 20 years of advancement in avionics and materials. The Chinese flanker has a modern glass cockpit, a multi-mode radar capable of firing active radar homing missiles like the PL-12, and extensive use of composite materials to save weight. The J-15 is what the Su-33 could have been if Russia had the funds to modernize it properly in the 2000s. Yet, even the J-15 suffers from the same fundamental physics problem, the ski jump. Chinese media often shows J-15s launching with light loads, reinforcing the fact that without a catapult, the heavy fighter concept is inherently handicapped. Comparing the Su-33 to Western contemporaries like the F-14 Tomcat or the F-A-18 Hornet reveals a divergence in philosophy. The F-14 was also a big, heavy interceptor, but the steam catapult allowed it to launch at maximum weight regardless of wind conditions. The Tomcat could carry 6 massive Phoenix missiles and a full bag of gas. The Su-33, launching from a ski jump, would struggle to carry a comparable load. The FA-18, while shorter ranged, offered true multi-role capability and a smaller deck footprint, allowing for a larger air wing and higher sortie rates. The Rafale M, perhaps the most aerodynamically refined of the bunch, manages to operate from a catapult carrier, the Charles de Gaulle, with a payload-to-weight ratio that shames the flanker, proving that smaller, denser designs often work better at sea. The legacy of the Su-33 is complex. In one sense, it is a failure. It was built in tiny numbers, suffered from a lack of modernization, and was ultimately slated for replacement by the smaller, cheaper, and more modern MiG-29K, the very aircraft it originally defeated in the selection competition. The Russian Navy realized that for a ship the size of the Kuznetsov, the MiG-29K makes more sense. It takes up less space, allows for a larger air wing, and its modern avionics make it a better multi-role platform. The Su-33 was a victim of its own ambition. It was designed for a supercarrier fleet that never materialized. The Ulyanovsk, the nuclear-powered supercarrier that would have had catapults and been the true home for the Su-33, was scrapped on the slipway in the 1990s. And yet, to dismiss the Su-33 as a failure is to miss the point of its existence. It proved that the Soviet aviation industry could solve the immense technical challenges of adapting a high-performance heavy fighter for carrier operations. The folding wings, the reinforced structure, the aerodynamics of the ski jump launch, these were massive engineering hurdles that Sukhoi cleared. The Su-33 remains the only aircraft in the world capable of performing the Cobra maneuver while carrying a full load of air-to-air missiles, though one hopes the pilot never tries this on final approach. It has a ruggedness and a raw mechanical charisma that modern computerized jets often lack. There is also the what-if of the Su-33UB, also known as Su-27KUB. This was a side-by-side two-seat trainer and combat variant that featured a completely redesigned wing with a larger area and adaptive leading edges. It was an aerodynamic marvel, promising even better payload and range performance. It demonstrated that the flanker airframe still had untapped potential for naval evolution. But like so many late Soviet projects, it died of financial starvation, leaving the Su-33 as a singular frozen branch of the flanker family tree. Today, the surviving Su-33s are being upgraded with the SVP-24 system and engine overhauls to keep them relevant, serving alongside the MiG-29Ks. They are the elder statesmen of the deck, the heavy hitters kept in reserve. They represent a specific vision of naval power, one where the sheer intimidation factor of a flanker appearing on the horizon was considered a weapon in itself. When you see a Su-33, you are looking at a heavyweight boxer trying to fight in a phone booth. It's awkward, it's constrained, but if it manages to connect, it's going to hurt. The Su-33 is a machine of paradoxes. It is an aerodynamic masterpiece compromised by its launch platform. It is a formidable dogfighter that rarely gets to fly with a full combat load. It is a symbol of Soviet might that spent most of its life rusting in port. But for the aviation enthusiast, it remains one of the most fascinating chapters in the history of flight, a testament to the audacity of engineers who looked at a 30-ton land-based interceptor and said, "Yes, we can put this on a boat." It reminds us that aviation is not just about the optimal solution. Sometimes it's about the most spectacular one. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.